In this lesson, we're going to learn what are polar bonds, what are nonpolar bonds, and then we're going to look at molecules that have polar bonds and ask ourselves the question of, just because a molecule has polar bonds, does that mean it has to be a polar molecule, or could it be a nonpolar molecule? Before we can get into that, you have to know what polar means. Polar means there are two poles. So if you think about our planet Earth has a north and a south pole. If you think about batteries have usually a positive side and a negative side. So anytime there are two different poles, we call those things polar. So the Earth is polar, batteries are polar, and bonds can be polar. One side of the bond can be more negative and the other side can be more positive. When poles don't exist, we call them nonpolar, which means you can't tell one end from another. Now that's with bonds, and those are easy to look at because when we look at bonds, we just have to look at which of our atoms is going to have a greater likelihood of attracting electrons. That's what's going to be negative, and the other is going to be positive. It's easy with bonds. What do we mean about molecules? What do we mean when we're saying nonpolar molecules or polar molecules? So we can look at bonds individually, like this one. We look at this bond individually, but we can also look at molecules as a whole, which means we look at the individual polar bonds, then we attach them together in a molecule and then ask ourselves, did anything change? Is the molecule still going to be polar or nonpolar? So we'll get there. We're not there quite yet. Let's first start off with the basics. We'll start off talking about what are nonpolar bonds. So we're starting with nonpolar bonds because those are easier to think about. Remember, nonpolar means there are no poles. You don't have a positive or a negative side. So how do we get nonpolar bonds? Usually when you have two of the same atom binding together. So in this first example, I have fluorine bound to itself. They're sharing a pair of electrons in the middle. Since both of them have the same electronegativity, we know that the same electronegativity means both of these fluorines have the same pull on those electrons. Think of this as a game of tug of war. If both of these fluorines were in a tug of war competition for those electrons, which fluorine would win? This has a strength of 4, that has a strength of 4, so they're equally strong, which means neither of them is going to win. Those electrons are going to stay just right in the middle, and if the electrons stay right in the middle, neither of the fluorine wins, so neither of the fluorine is going to have that partial negative charge that comes with having electrons closer to them. Okay, let's look at another example. Let's look at hydrogen. Here also we have a tug of war. There are fewer lone pairs and electrons around each hydrogen, but our focus is these two central electrons that are being shared between the two hydrogens. This has a strength of 2.1. This has a strength of 2.1. So it's obvious hydrogen is weaker than fluorine in terms of electronegativity, which means if hydrogen and fluorine went head to head, fluorine would win. But that's not what's happening here. Hydrogen is going head to head with another hydrogen. So when we look at that, both of the hydrogens are equally matched in this tug of war competition for electrons, which means neither hydrogen gets the prize, which means both of the hydrogens just remain neutral, leaving this a nonpolar bond because their electronegativities are the same. You just need similar electronegativities to have a polar bond. But does it always have to be two of the same element? Can it ever be two different elements and still have a nonpolar bond? The answer is yes, as long as their electronegativities match. So in this example, we have carbon and we have sulfur. Carbon and sulfur both have approximately an electronegativity value of 2.5 each. So this bond is nonpolar, even though those two atoms are different from each other, simply because they have the same electronegativity, which means if this were a tug of war, a competition for these electrons, because remember the bond is just shared electron, both of these would tie because they have the same strength and neither one is going to pull stronger than the other. So this is a nonpolar bond. How can you tell if a bond is nonpolar when it's two different atoms and I haven't given you the electronegativities? You can't. It's not possible unless you memorize the whole electronegativity chart. And that just seems silly, so you don't have to memorize the chart. For the purposes of this class, we will only be looking at nonpolar bonds in terms of the same atoms are bonded to each other, therefore they have the same electronegativities, and that is a nonpolar bond. All right, so we said that when hydrogen is matched up to itself, there is no winner because they're both equally strong. And then I said that if hydrogen was matched up to fluorine, then fluorine would be stronger, and fluorine gets to be the winner. What happens when that happens? So let's actually match up hydrogen and fluorine and see what happens. We end up with a polar bond. And what we mean by a polar bond is now I have atoms with two different electronegativities. So this has an electronegativity of 4. This has an electronegativity of 2.1. Think about which one is higher, which one is stronger. 4 is stronger, which means these two electrons in the center, which technically one came from hydrogen, one came from fluorine, these two are more strongly attracted to the fluorine than they are to hydrogen. So if this was a tug of war competition for these two electrons between fluorine and hydrogen, fluorine would win because it's more electronegative. So what does it mean to be the winner of this particular competition? What's the prize? Well, whichever element is more electronegative, we put this sign next to it. This is a lowercase delta. It stands for partial negative charge. So in this bond, this side is slightly negatively charged. This side is slightly positively charged. Notice how it's not a complete positive or negative. It's not like +1 and -1. It's only partial, only slight, because fluorine is not actually stealing the electrons. It's just holding the electrons closer to itself. That's all. So when we have polar bonds, remember, poles means you have two different poles. Here's the negative pole, here's the positive pole. Partial negative pole, partial positive pole. So that's an example with hydrogen fluoride. Let's look at a different example. Let's say pick two other elements, beryllium and fluorine. Well, beryllium is even lower in its electronegativity compared to hydrogen, so this is an even bigger difference, which means beryllium and fluorine, when they're bonded like this bond is considered to be polar, with fluorine being partially negative and beryllium being partially positive. Let's look at a third example, boron and fluorine. Now, these are almost the same electronegativity difference as hydrogen and fluorine, but still fluorine is winning out because fluorine is the most electronegative element on our periodic table. So between boron and fluorine, fluorine wins out because it's more electronegative, and therefore fluorine has the partially negative charge, whereas boron has the partial positive charge. So far, what we've looked at are only individual bonds. Like if I have two atoms and I combine them with a bond, then how can you tell if that bond is polar or nonpolar? There's very little value to knowing whether a bond is polar or nonpolar unless this is the molecule, like this is it, hydrogen fluoride. Nothing else is going to be added. This is polar. That's good to know. Not just the bond, the molecule is also polar. But what about for bigger molecules? Like for example, with beryllium and fluorine, something is missing here because beryllium can form another bond. Same way with boron, something is missing here and here. Okay, so I know these bonds are polar, but what happens when I fill in these gaps? So let's go ahead and try to fill in these gaps. And there are a couple of different ways in which we can fill these gaps in by giving the molecule multiple polar bonds. So let me start off with beryllium. So we started off with beryllium and fluorine just to see if that bond was polar or nonpolar. Let me go ahead and complete the molecule. Here's what the completed molecule looks like, beryllium fluoride. Fluorine is still very electronegative on both sides, and so each fluorine is pulling these electrons. So now think of it as a tug of war between the fluorines, and the prize is beryllium's shared electrons. Now what? Now in this case, because this is a polar bond going this way, and this is a polar bond going this way, the two end up canceling each other out. What does it mean to cancel each other out? It means this molecule is nonpolar. So notice the important difference. Polar bond, that's why there's a tug. Polar bond, that's why there's a tug. So these two are polar bonds, but they're placed right opposite to each other, so they cancel each other out, making this molecule overall nonpolar. So for this molecule, I cannot find a positive end or a negative end because both of these cancel each other out. Now, this is easy to visualize because in most tug of wars, you have one person on this side, one person on the other side, and you can easily tell who is going to win. And if both of them are equally strong, you know it's going to be a tie. So this is easy for a linear molecule. Now, what if my molecule wasn't linear? What if I go back to boron and fluorine, where we know there are two bonds missing, and go ahead and fill those in now? So this is boron trifluoride. So in this, I know that fluorine, fluorine, and fluorine are all very electronegative, and they're all pulling on those electrons in their respective directions. So now this is a three-way tug of war. In this three-way tug of war, who's going to win? Well, nobody, because fluorine, fluorine, and fluorine, they're all equally strong, and they are all equally angled from each other. They're each at a 120-degree angle from each other. So imagine if we had a prize in the middle and three equally strong people were pulling from these angles. Who would win? The answer is nobody, because there's an equal pull on all sides. So this is also a nonpolar molecule. But watch out, it's a nonpolar molecule, but notice how it has polar bonds. So it has one polar bond, two polar bonds, three polar bonds. It's just they're arranged in such a way that they cancel each other out. We call this symmetrical, which means there's a certain pattern to it. Okay, we saw what if we have a tug of war between two? What if we have a tug of war between three? Now, what if we have a tug of war between four? So here I have carbon with four fluorines, but notice how I've drawn it with the dashed lines and the solid line. Think about why I've done that. That's because this molecule is three-dimensional. How do I show this on paper? I can't. So to give this molecule some depth, here's how you should read it. The two solid lines over here are these two bonds, which are right along the plane of the paper. The dashed line is behind the paper, and then this solid line, the stronger solid line sticking out, is in front of the paper over here. Now, if you look at this, in all cases, fluorine wins in the electronegativity battle. So between carbon and fluorine, fluorine is more electronegative. So this is polar, this is polar, this is polar, and this is polar. But what about the overall molecule itself? The overall molecule itself is nonpolar because they're all pulling at a 109.5-degree angle. So they all cancel each other out, and this molecule becomes nonpolar. So how do you know when you have nonpolar molecules? So when we have identical polar bonds that are arranged symmetrically, the entire molecule is nonpolar. What do we mean by identical polar bonds? We have boron to fluorine, boron to fluorine, boron to fluorine. So everywhere it's boron to fluorine. So they're the same bonds with the same differences in electronegativity, but they're symmetrical in this pattern, 120-degree angle from each other. Same way here, it was carbon, fluorine, carbon, fluorine, carbon, fluorine, and carbon, fluorine. So they are identical bonds, as in it's the same difference in electronegativity, but they're arranged symmetrically around the central atom, and so the entire molecule ended up being nonpolar. Okay, so how do you create a polar molecule, and what do those look like? How do we represent those? So how are polar molecules formed? Polar bonds are, when they're arranged asymmetrically, you end up getting a polar molecule. So think back to this, BF3. The reason that this was nonpolar was because I had the same bond on all three sides and it was an equal angle. Let's say I take one of these now and replace it with a hydrogen that has a lower electronegativity. So now I have this instead. Now, if you look at this molecule, we know that fluorine is going to have a strong pull on those electrons, but hydrogen is weak. It cannot keep up with the fluorine. So fluorine ends up winning. And if fluorine wins, we mean that that end of the molecule, so this entire end of the molecule has a partial negative charge, whereas this entire end of the molecule has a partial positive charge because now the electrons are being pulled asymmetrically, like these two fluorines win in a tug of war, and this hydrogen is not able to keep up with those two fluorines. So we have negative over here, positive over here, making this a polar molecule. Let's go ahead and take a look at this next one here. So basically I have carbon with a bunch of different hydrogens, but instead of having all of them as hydrogen, one of them is a fluorine. So let me go ahead and put a fluorine atom over here. Now suddenly this is asymmetrical because you can see that one side is different from the others. So when I look at this molecule right now, I can see that this side is going to pull the electrons more than this, or this, which means this side is partially negative, this side is partially positive. So this entire side of the molecule is positive, this side is negative. So this is a polar molecule because I have a negative side and I have a positive side. Partial negative, partial positive. So the asymmetry here comes from the fact that even though my molecule itself looks symmetrical, one of the atoms got replaced. So I have different bonds that are around the central atom. So I have carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, but wait, carbon, fluorine. There's the asymmetry. Same way in the previous example, we had boron, fluorine, but hang on a second, boron, hydrogen, asymmetry. And now we have a polar molecule. There's another way in which molecules can get their asymmetry. So let's look at this one. Over here, we have nitrogen with 3 hydrogens. So these are all the same bond. Nitrogen, hydrogen, nitrogen, hydrogen, nitrogen, hydrogen. They're all the same bond. The asymmetry comes in the way that the molecule is set up. So you have hydrogens at the bottom, the nitrogen is at the top. This is asymmetrical because the nitrogen is more electronegative and pulling all of these towards the top, towards itself. So they're all moving towards the top. So the bottom of this molecule here is partially positive, whereas the top of the molecule here is partially negative. So since just like a battery, I have a positive and a negative side, this is a polar molecule. So in this case, the asymmetry didn't come from the fact that I have different bonds. It came from the fact that its 3-dimensional structure didn't have anything to balance out here at the top. If I could have had one more thing to balance it out at the top, so hypothetically, if I could have had this, then it would have been a non-polar molecule. But since there was nothing like that over there, this ends up being a polar molecule.